It's a pleasure for me to introduce Giorgio Vacchiano is a professor at the University of Milan. He's an expert of forest and planning, planning and management. And it's really a pleasure for me and as for all of us and Angelo Facchini to have him with us, because he's currently collaborating with us on some micro projects that are about research on urban green. Maybe we can ask Angelo to give some details about it.
Oh, yes. So this seminar is a part of the outputs that are being provided by the micro project led by MT on the analysis of urban green and under the point of view of the computer side and automation side. So the idea is to provide a background and a literature review and a review of the methods that are used to identify and classify urban green. And this micro project is part of the preparatory activities that will be performed on field next year, when the So Big Data team will involve citizens in a field experiment focused on the municipality of Pisa, which means the classification of trees and green areas in the urban environment. And the idea is to mix the two approaches. So from one side, involve citizens in taking pictures and measuring trees and urban areas. From the other side, to tune algorithms for a better identification of the urban green. This micro-project is also in convergence with another micro-project led by ISTI CNR. And also this micro-project will be objective of a memorandum of understanding that is going to be signed between the municipality of Pisa and the So Big Data Consortium. So this is only the first step of an activity that will be developed in the next 2 years. It's a pleasure to have Giorgio, just because he's one of the most influential and leading expert in this field in Italy, and he has a strong background on all the activities that will be performed on urban green in the next years. More importantly, this is also an activity that is in full convergence with the recently published biodiversity strategy from the EU. And under the environmental and economic point of view, it is important because it's a step further to better classify and to better assess the value of the natural capital that is currently present in cities. So I can leave the field to Giorgio, che non vedo. And probably the talk is tuned in about 40 minutes, 45 minutes. And after the talk, we expect 15 to 20 minutes of question and answer session. So Giorgio, the field is yours.
Thank you, Angelo. Let me share my screen so that I can start by illustrating today's topic. So good evening, everyone. Thank you for coming to this meeting. This talk will be about automated methods for urban green analysis. In the context of one of the micro projects of So Big Data, we have just finalized a summary report about the most recent developments in research regarding how to assess the size, the location, and the status of urban green, urban forests, and trees with automated methods. Why are we interested in this? Well, the context is the relationship between cities and climate change. And cities and climate change currently interact in two ways. Obviously, cities are a place of high vulnerability to climate change. So adaptation must take place in order to avoid the worst impacts of climate change. We'll see them in a minute. But also, cities are currently one of the main emitters of greenhouse gas in the world. The main problem about this is that the urban population is rapidly rising, and it's expected to reach 70% of overall global population by mid-century. Already now, 55% of global population lives in cities. And as I was saying before, the high majority of greenhouse gas emissions is produced by cities or in cities, 75% of global emissions. And at the same time, most of global cities, including European ones, suffer from impacts of climate change. Green infrastructure are key in both these issues. They can help with climate change mitigation, as we know, by sequestering quantities of carbon and CO2, removing them from the atmosphere. But also, they provide a lot of benefits in terms of adaptation to whatever effects of climate change we will experience anyway in the next years. And this adaptation is specifically targeted to several aspects of human well-being in cities, both involving environmental well-being, so living in hot temperatures or coping with intense storms and rainfall. We just had a big hailstorm here in Turin 5 minutes ago. And also with mental and so even social well-being. If we take, for example, the metropolitan areas of Milan, which we see pictured here, we immediately recognize the most urbanized area by looking, for example, at a map of maximum temperature, in this case, maximum night temperatures. We know about an effect called the urban heat island, by which temperatures increase inside the most densely populated urban area. In fact, we really can see almost the streets of Milan by just looking at a temperature map here. The same goes for other effects of climate change, such as the runoff of stormwater. Storm events are becoming more frequent, more intense, and in cities which are covered by impervious ground, rainfall water must go somewhere. It doesn't infiltrate the soil, it tends to run off on the surface, and where it can cause a lot of damage. And even looking at this kind of variable, we can readily see where the denser urban areas are located. And this is the same even for another threat, not directly related to climate change, but interacting with it. And this is pollution. This is specifically a map of PM10, so particulate matter pollution. And what you're seeing here is the number of days in a typical year when particulate matter concentrations were higher than the threshold recommended by Italian law. The reddest, the highest number of days with high pollution or pollution higher than regulatory thresholds. And even in this case, the urban area is readily recognizable. Now, if we couple this with a map of urban tree canopy cover, we can see what's happening. The urban area in the center of the map that was subject to the highest temperatures, the strongest runoff, and the highest pollution is also the most devoid of urban trees and forest. You can recognize some parks at the edge of this map, some protected areas, some natural parks, even river corridors, such as the Ticino River on the left side of the picture. But the central area is really devoid of trees. But trees can really help with all these threats. They can provide shade and evapotranspiration and thereby cool off high temperatures. They can intercept incoming rain and therefore delay flooding peaks and lower the risk of catastrophic flooding damage from runoff. And they can also absorb on leaf surface particulate matter and other chemical pollutants, such as nitrous oxides or ozone, for example. So apart from absorbing carbon, which is what we usually think about, green infrastructures and trees in urban settlements are highly important for urban adaptation to climate change and environmental quality. So we have to know a lot of details about where urban trees are in order to be able to assess their impact and possibly plan an improvement of their functions. Urban planning nowadays cannot go without correctly planning new green infrastructures. There are a lot of cities in the world and in Europe that are planning new urban forests, new urban trees with highly ambitious targets. But the first step in order to do so is to gain a good knowledge of what's already existing. And this means being able to measure or assess the species of the trees, because different species have different characteristics, traits, ecological traits, leaf area, for example, height, crown area, affect all these ecosystem services that trees can provide in cities, such as CO2 uptake, rainfall interception, and absorption of pollutants. We also need to know the size of the trees, the diameter of the stem, the height of the tree, the area of the crown. Even within the same species, these variables, in fact, influence and affect by great values the ecosystem services that urban trees can provide, and also determine what can be considered as risks of this or these services of trees, such as mechanical instability under strong winds. And finally, of course, we need to know where these trees or urban green areas are located. This makes all the difference, not only because a large and continuous green area is functionally different than just sparse individual trees, for example, for cooling effects, but also because the spatial distribution of trees determine whether the citizen can have equal access to green areas. And if we have a lot of trees in a cities, but they are unequally distributed, we know that not all citizens will be able to take advantage from their benefits. So this is another very important variable to be able to know. And finally, not all trees stay healthy for their life, especially in urban settlements where they are exposed to different kinds of stress, from pollution, storm damage, soil compaction from cars or pedestrians, damage from public works, and drought and heat. So we need to be able to monitor measures and also to monitor. Cities that have managed to do so are able not only to plan their new infrastructure, green infrastructure correctly, but also to measure the economic value urban forest. Services in urban trees comes from the United States. We will see what kind of models, what kind of tools are used to obtain these estimates. But it's interesting because in most American cities, urban trees provide values higher than $6, $8, or even $20 million per year to the whole community in terms of avoided flood damage, avoided health costs, increased value of properties, and of course, CO2 and pollutants sequestration. Now, measuring manually all trees in a city is not feasible. They're not many, but they are many enough that it's impractical to measure them. Of course, we can use some statistical approaches. We can carry out a forest inventory, just as we do in rural or mountain areas. and then upscale the results by using some statistical indicators. But another way to get a good knowledge of green infrastructures in cities is by using, for example, remote sensing tools. You know, there are several satellites orbiting the Earth that differ between one another for resolution, typically spatial and spectral resolution, so the kinds of signal that they are able to get from the surface, return time, return interval around the same place, cost or availability of imagery. So the first part of our report has summarized how satellite images have been used recently in the last 2 years to assess tree size, tree species, and tree location and health status in urban forests. So we provide just a few examples, maybe one example for each of the target variables of interest. And then I will point you out to the full report if you want to read more examples and maybe imitate them in the activities that you're responsible for. So the first and foremost variable that we are interested in reconstructing is urban land cover. That means classifying the area occupied by a city in different categories. Here, for example, we see a distinction between agricultural and fallow land, the built-up area, sand or water, and vegetation, which might be the most interesting variable for our purposes. And remote sensing satellite imagery can be used, and has been used since a long time now, for classifying urban land cover. How to do that? Well, you need to train some sort of computer-based classifier, some algorithm that uses the data contained in the satellite imagery to recognize and tell apart these different land cover classes. In this study carried out in a peri-urban area in India, for example, 6 of these classifications algorithms have been compared based on Landsat imagery. Landsat is the oldest running and longest running satellite that we have orbiting the Earth. The several iterations of Landsat satellites are orbiting the Earth since the mid-70s. So Landsat imagery forms a really long time series that we can use also to check for temporal changes in our variables of interest. You see here the 6 different machine learning algorithms that have been used to train the computer to use the Landsat image and check for the presence of these different land cover classes. The results typically obtainable by these techniques are quite accurate. Of course, it depends on how much detail you want to add to your categories. Here, 6 land cover classes, you can have 60, and of course, accuracy will decrease by some amount. But here, for example, we have 90% accuracy when assessed by a set of validation points randomly drawn on the landscape of interest. But knowing that vegetation is here and there or there obviously is not enough. We want to know in more detail, as I said, the location possibly of individual trees and their size. And there are several studies that try to assess individual location of single trees in a city. You see here just one example. And of course, in order to pinpoint individual trees, you need a much finer image from satellite. So Landsat or MODIS, which has an even larger ground footprint, are not suitable for this purpose. You need very high resolution satellite imagery, which often is not available for free. In this study, for example, World View satellites 2 and 3 were used with a ground resolution of 30 centimeters. So quite detailed, 100 times more detailed than the previous example. And the individual trees were recognized. They tried to recognize individual trees, again, with some statistical algorithm. First, in order to detect green areas based on different spectral bands in the satellite imagery, so green versus red, for example. And then they instructed the computer to delineate the crowns of individual trees and find out their center, their geometric center. And this is supposed to be a location of a tree stem. For example, in this study, as you see, 85% of trees were correctly identified, but there was a 23% omission error. So trees that existed, but were not detected. One interesting conclusion from this study is that this algorithm works better if run on images taken during autumn, possibly for a better distinction between the color of autumn trees and the urban background. Beyond the location of individual trees, we might be interested in the size of the tree. And here is a study not carried out in a city, but the techniques can be adapted readily for urban studies. It was one of the largest studies, the most important studies published last year on Nature journal. So a very, very important scientific journal. And the same satellites were used, as you see, WorldView 2 and 3, together with some other very high resolution satellites like GOI-1, with a ground resolution of 50 centimeters, so 0.5 meters this time. But the technique was applied on a very large scale. Almost 2 billion individual trees were assessed, were detected on 11,000 images covering most of the Sahel area. So most of the North Central African continent was subject to individual tree detection. A similar statistical technique was used to identify individual crowns. Of course, this is all automated by the computer. What kinds of accuracy can we reach today? Well, the authors of the study claim that they correctly identified all canopy clumps larger than 200 square meters. So instead of talking about individual trees, we talk about groups of trees. And if a group of trees is larger than 200 square meters, then it was certainly recognized by the satellites. Speaking of individual trees, we still have problems with the smallest ones. So 5% of the trees were not detected, mostly smaller than 15 square meters. That's a very small tree, especially for a city. And 25% of tree area, so the ground area covered by trees, was not detected, mostly for trees smaller than 50 square meters. So these kind of techniques are promising in cities because, with the exception maybe of new plantations, urban trees tend to be larger than these size ratios, larger than 15 or 50 square meters with their crown. So I think that by automating these kind of routines and analysis, detection of tree location and crown area can be successful in cities. Another aspect, another variable that we are interested in is the height of the trees. Not a lot of studies exist that analyze tree height in cities. However, a different kinds of satellites has been used for analyzing the heights of forests, so a rural or natural context. And specifically, I'm talking here of a spaceborne LiDAR system, which is called JEDI. JEDI was launched only 2 years ago, so it's a very recent development, a very recent program by NASA. It has a ground footprint of 17 to 25 meters, so it's not able to detect individual trees, but clumps of trees mostly. And its signal is sent down on a regular grid with spacing between 200 meters and 2.5 kilometers. So maybe it's hardly applicable to a city because the space between two different points is quite large. Preliminary studies, however, are interested in understanding what kind of accuracy this satellite can give us in measuring tree height. And this is an active satellite, so it's not limited to detecting reflectance by the Earth's surface, but it sends out a signal, a laser signal, and detects the return impulse. And by analyzing this impulse, is able to differentiate between tree and ground, and therefore to calculate the height of the tree. Currently, this signal is not very accurate, especially for very tall trees. So the height is saturated above 30 meters. So if a tree is 30, 40, or 50 meters high, the satellite is not able to tell the difference. And the mean error when using local calibration, this is a global study. So in fact, you can go to the links in this slide and download a map of the height of global forests. The current mean error is between 6 and 9 meters, which, if maximum height is 30 meters, is not a very good performance, I would say. So maybe in the future, this signal and the analysis techniques will improve, but at the moment, this is not reliable enough for detailed analysis in urban areas. Of course, I mentioned tree species, but how can we detect tree species from remote sensing, from satellite? Well, there are different ways to do that. The most common ones is to use not one single image, but a time series of images in order to see the change in color and reflectance of tree canopies. So if we calibrate a reflectance curve or spectral curves through time, the houses and streets stay the same and the color of the crowns changes with fall, with winter. So we might be able, with an appropriate ground truth data set, to classify species or genera between one another. And this example, for example, was applied in Washington, D.C. in the United States, where the calibration data set consisted of more than 16,000 ground points. Washington has a very accurate urban tree inventory, so with ground-based measurements, with locations and species. And this was used to train, again, a statistical algorithm, a machine learning, in this case called random forest. What kind of accuracy? Well, it depends, again, on the level of detail that you're interested in. When classifying 19 species, accuracy was not very high, 60%. If you're content of classifying genera, however, so 10 genera, the accuracy increased to 70%, 73%. Again, with using very high resolution satellite images like WorldView 3. These kinds of satellites can be also integrated with one another. So you can fuse together, merge optical passive satellites based on spectral reflections and active sensors such as LiDAR, the JEDI that we mentioned. Because it might be the case that one kind of data could be available for a large area, for example, spectral indices, but it may not be a very strong predictor of the variables that you're interested in. And at the same time, you may have a very good predictor, such as LiDAR data, available only on a small chunk of land. So you can merge the two and use one as a calibration for the other, but correct statistical estimators must be used because none of them is you can consider as the truth. So both represent some kind of statistical sampling, and you have to take this into account in your statistical analysis in order to obtain correct estimate. But this can be done. So you can kind of generalize the signal by LiDAR using optical images over large scales. What are the take-home points for this? That was the main category of the report. Freely available satellites at coarse resolution are good for fast analysis, maybe of land cover and land use, but of course, they cannot arrive at an individual tree level. For this, you need very high resolution imagery, such as that provided by WorldView satellites, smaller than 1 meter ground footprint. LiDAR, so laser and active sensor, can be used to recognize individual trees or identify treetops and tree height, of course. And in order to identify what a tree is, there are algorithms that work better than others, and these are called object-based algorithms. So teaching to the computer to recognize a tree based on a group of pixels rather than just one pixel by one. This doesn't work very well. Ancillary data can help a lot in improving accuracy. Digital elevation models, texture, color, this can be used and can be inserted in statistical models. And multi-temporal images are very important if you want to identify tree species. And by the way, fully automated tree counting has never been performed. So you still need a manual phase, either for calibration or validation of your statistics. You cannot just take an image, run it, and have your tree count. This, we're not there yet. I'll be shorter now. Some other examples of automated analysis of tree variables in city can be provided by using unmanned area vehicles, UAVs or drones. But drones can be equipped with different sensors. And also here we have a double option. We can use optical sensors, or we can use active sensors that send out a laser impulse. But even just using the optical reflectance with drones, we can get very detailed images and analysis by using a technique that's called structure for motion photogrammetry. Structure for motion photogrammetry is based on a 3D reconstruction coming from an overlap of two different images taken by a drone, even commercial drones. In this paper, for example, a DJI Mavic Pro was used. This is the same drone that I have for leisure and that I use when I go in the forest to take some movies or photos. With a very simple camera and a very simple flying system. A common cell phone was used to pilot the drone. Of course, you have to put in place a flying plan in order to ensure that the overlap between images happens. We're talking here about 80 or 90% overlap. So these two images are really overlapping a lot to one another. And by analyzing the two overlapping images with some specific software, you were able to reconstruct the 3D profile of the surface you are flying above. And with it, to recognize tree height and also possibly tree diameter. In the study in Illinois, for example, the mean error in tree height was reduced to 2 meters, which is already quite good. And the error in tree diameter was only 3 centimeters. So a quite good estimate of tree diameter there. Interesting information, the estimate worked much better with leaves on and much worse with leaves off. So during the winter, it's not recommended to carry out this kind of analysis. Of course, once you have a 3D reconstruction of your canopy, your urban canopy, you can also calculate the size of the tree crown, the diameter, the area, and even the volume of the crown, which can be a very important variable, for example, to estimate the interception of incoming rainfall. This is an example taken from the city of Melbourne, which has designed its own drone system. So this is not a commercial drone. This was specifically designed for the purpose. And it was equipped with both a LiDAR and an optical sensor to be used with structure for motion photogrammetry. And the two results were compared to one another. Of course, LiDAR was thought to be very much precise, more precise than everything else. But structure for motion delivered almost the same level of accuracy. In fact, the degree of association, the correlation between the two kinds of measurements was always higher than 95%. And in the end, drones can also be used to identify species. So instead of relying on satellite images, you can fly a drone. In this case, a fixed wing system, so a drone that's able to fly longer distances and longer times. And again, by combining optical reflectance and point clouds coming from this 3D reconstruction, the authors of this study in China were able to recognize 3 species with an 82% accuracy. Again, with different machine learning algorithms to teach to the computer how to recognize where individual trees were and what kind of species they were. In this case, the whole set of species was 8 species. But if it's enough for you to recognize coniferous versus deciduous species, the accuracy obviously is much higher. These kind of laser impulses can also be cut from the ground. So there are systems called terrestrial laser scanning. Instead of sending impulses from a drone or even from satellites, these are mobile stations that can be transported around the city and shoot their laser beams towards trees from ground level. And with this technique, even larger accuracy, even higher accuracy can be obtained. For example, in this study, looking at tree height and diameter, the mean error in tree height was lower than 40 centimeters in most occasions. And tree diameter was not very easily recognized, mostly because it's not exposed to the whole inputs of laser beams. So there are statistical techniques needed to reconstruct the invisible portions of tree diameter. So this technique is very useful for tree height if you can afford this kind of tool. The cost can be higher than 50,000 euros, so it's not for everyone. Another technique that uses street level images is currently growing in research interest. You know that we have a global data set freely available of ground level images. It's Google Street View. So more and more research is being based on downloading full sets of urban street view imagery by using the freely available Google API to detect at least the location, not the size, but at least the location of green infrastructures. For example, by recognizing what's green and what's not green in a picture, and then putting together all the pictures taken in all perspectives, so 360 degrees around the same point, and then taking the ratio between the green pixels and all the other pixels. This produces a map for all points where Google Images can be downloaded from, of the percent of green area when looking around a certain direction. And by putting together this map, you can come up with basically canopy cover or green canopy cover in selected points around the city. Of course, the most important information here is the distance between one image and the other. In this study, for example, images taken further than 20 meters apart were not accurate anymore to reconstruct the amount of green and location of green infrastructures. And there are more recent developments using Google Street View images, more sophisticated statistical algorithms to recognize the trees, surveys for tree mortality, so checking for tree health and tree vitality on these images, and also studies that integrate these Google Street View images with the remote sensing approaches that we have talked before to increase accuracy and generalize the location of the green infrastructures. Finally, and then coming to the conclusions, our report took a look at the models and apps that are available for automated or semi-automated monitoring of urban trees, also using citizen science approaches. Models. So why using models? Well, we have talked so far of basically a snapshot approach. So we can reconstruct what's there now, but we are also interested in what will be there in the future. How will these trees grow? How large they will come? How healthy they will be in a given climate, for example. And there are some studies that have calibrated models, for example, of tree growth. One is City Tree. City Tree was calibrated in 6 European cities for 4 main tree species, so not a lot. Linden, locust, platanus, and esculus, and horse chestnut. It is a physiologically based growth model. So it takes climate parameters and environmental parameters, and is able to calculate how much photosynthesis each tree is able to carry out. From this, you can calculate growth rates, carbon sink, carbon being stored during photosynthesis, transpiration, runoff, shading, and cooling effects. So a lot of the ecosystem services that we mentioned at the beginning of the talk. Based on simple field measurements such as diameter and height, which can also be derived from remote sensing, as we have seen before, simulations can be carried out also under different climate change scenarios and CO2 atmospheric concentrations to check what will be the trajectory of growth of the trees under future climates in our cities. And then finally, a look at available apps. There are some websites and apps that are coming up for monitoring urban trees. And as I said, most of them make use of a citizen science approach. So they provide a platform to the citizen to be able to monitor the size and status and location of urban trees. And then they collect all the data and they make them available to the public, much like OpenStreetMap does for example, street maps, in fact. These are screenshots from the OpenTreeMap website, but the app works in a similar way. You can in fact download the app. It's freely downloadable, and you can start geotagging trees in your city. So citizens can geotag trees. They can take pictures of them. They can recognize the species. And in the end, what comes up is a crowdsourced map of urban trees. Currently, these are available only for US cities. So this is a limitation, of course. But the app has some models in the background that are able to estimate also the benefits of the trees based on their location, size, and species, as you see in this screenshot. And also the app has recently been made able to recognize the best areas for planting new trees in cities, based both on environmental variables and on social variables. So where's the higher population density, where's the higher vulnerability to heat damage to health, for example, where the elderly population lives, and so on. One of the most used models in the US is called i3. i3 is in fact a suite of different models. It's again based on ground measurements, so on measurements of tree diameter, species, and height, both carried out by inventory or by the remote sensing approaches that we mentioned before. And then it has some models in the background, statistical models that link tree size and species to the environmental benefits of the trees. Carbon sink, air quality or pollution sequestration, avoided runoff, cooling effect, and also the economic value of all these services. The approach is quite simple. Some easy variables are measured and then used to statistically estimate the foliage and the wood volume of individual trees. The total leaf area is assessed by the model using species-specific equation, which must be calibrated on the species of interest. And then the benefits are calculated, mostly based on the leaf area. So as I said at the beginning, crown size and leaf area is possibly the most important variable to be able to get a correct estimation of ecosystem benefits by urban trees. The i3 platform is growing, is ever growing. One of the most recent additions is called i3 Hydro. i3 Hydro is a fully coupled hydrological model that models not only tree growth and benefit, but also the water cycle in urban settlements. And i3 Hydro can be used, in fact, for highly detailed estimations of interception of rainfall by trees, runoff in urban settlements, load into sewers or the runoff system, and flood risk in forested or non-forested settlements. And finally, and these are my last two slides, the approaches using remote sensing at local or global scale are being made available, at least the results are being made available on websites. One of the most popular ones is called Treepedia. Treepedia actually uses automatic algorithms to classify individual trees and detect individual trees from remote sensing imagery. The results are available. You can watch them on the website. Are available for mostly US cities, if I remember correctly. The interesting thing is that, as I said at the beginning, tree location is then used to come up with a green view index score. So a score that expresses for every possible location in a city, how green that block, that neighborhood, that angle of the city is relative to the distribution of green areas in the city itself. And finally, a platform called opentrees.org that collects instead tree inventory by cities. So several cities make available on their official website the inventory, the survey of urban trees. Some of these are collected by opentrees.org. You see 226 sources in 20 different countries. There are even a couple of Italian cities. If I remember correctly, Bologna is the only Italian city currently present here. But also in Italy, there are different cities that have a public inventory, a publicly available inventory of urban trees on their official website. Florence, for example, Turin, Milan to some extent, and I think Pisa as well. So that was all on my side. I invite you to read the full report that I guess will be published on the So Big Data project website. And if you have any questions, you can of course ask them now or find me at my email or website addresses. Thank you.
So thank you very much, Giorgio. It's a quite interesting presentation. It's a quite complete review of all the methods that are, as of today, at the cutting edge of this topic. So if there are some questions from the participants. Unmute your mic, please.
Sorry, I'm Simona. Sorry, there is Emma. Okay, I just asked a question, the millennium question. Giorgio, in your opinion, if you would have, you mentioned, for example, Pisa, Bologna, other cities in the world, they have, this is, I understand, a very detailed database with information about size, species, and location of urban trees, and maybe also other plants. If you imagine you can work on such a database in a city of all the methods that you described us, so from drones to satellite and anything, where would you start if you want to help, I mean, a cross-analysis, so something that can foster the validation of automatic data? I mean, the last target, the dream would be, okay, we would like to make faster as possible the support to automatic systems, so we can then perform better policies and so on for climate change.
Well, it also depends on budget available, and I mean time and resources. The first step I would take is using satellite imagery. So I would not immediately go to more expensive and more lengthy techniques such as drones or terrestrial laser scanning. By using very high resolution satellite imagery and couple them with an accurate ground-based inventory, I think a good automated system can be put in place to monitor tree health, tree size through time. So the recurrence interval of these satellite imagery is high enough that you can in fact analyze very many images for every year. So for every year, yearly, you can have estimates of the evolution of the trees in your city if you have a good calibration data set, and this would be the ground inventory with precise locations. And the accuracy of the local geographical location is very important if you have to couple them with satellite imagery. And then using the whole time series, for example, to monitor health or changes in the urban tree area. Using Google Street View images is another promising avenue, but at the moment it's not able, this approach is not able to assess quantitative variables. So no tree height, no canopy width, no tree diameter, only maybe green cover. So this is also obtainable for much cheaper analysis of freely available satellites. So I think this technique is not developed enough yet.
Thank you very much.
So there is Emma.
Hi, Giorgio. Thank you very much for your presentation and for your previous answer, which is a nice segue to my question, which is specifically about the use of Google Street View.
Right.
For the automated analysis of urban green, but also the analysis of cities in general from a townscape view or a street level view or eye height view. We're working on a project that is a little, in a way, is combining the automated analysis of urban green through remote techniques like Google Street View and satellite view, and a citizen-led data collection strategy, in the sense that we are looking to expand the territory covered by Google Street View in cities that don't have a complete Street View map, and to access parts of the city that Google or volunteer citizens have not yet covered, which tend to be spaces that are not accessible with the car. So we are thinking of often green spaces, pedestrian areas, parks with paths. So we are looking to involve citizens to complete the Google Street View in a crowdsourced way. But at the same time, we are asking ourselves, what is the, let's say, fitness of this data set for automated analyses such as that of urban green? How can we make that the street view imagery that we collect more useful than the current Google Street View? What is really the missing piece to get to tree species, tree height, very rigorous geolocation? Is it simply a question of resolution that you mentioned, a minimum spacing of 20 meters previously? Is it a lack of algorithms that can identify tree species? What would you say is the leap that needs to be made?
I think it's inherent limitations in the oblique imagery approach. So the Google Street View photos or the citizen taken photos. So this approach by itself is able to deliver data on urban green cover and possibly tree location. There is another study just come up this year. Maybe I can put the link here in the chat. In the Metro Vancouver area in Canada and in Pasadena in the United States, using more than 30,000 images from Google Street View, that was able to detect 70% of all trees with a mean error in position between 4 and 6 meters. So I would say much less accurate than what you can get by analyzing tree locations using very high resolution satellite imagery. But of course it's free, so it's a trade-off there. However, this kind of images is inherently unable to deliver on tree size, crown size, and tree height, and species identification. So there's no way at the moment to obtain an automated analysis of these variables. If you want this, you have to couple in some way these images with other data sources. So other more traditionally remotely sensed images for tree height, for example, so LiDAR data, even freely available ones such as IceSat or JEDI, even if the resolution is not very high, maybe coupling with Google Street View can be effective. For species identification, one way would be to obtain a time series of Google Street View analysis in order to, again, analyze a spectral curve through time of tree color or spectral indices in the same frame, in the same image. Unfortunately, the Google API currently does not support multi-temporal images. So you're not able in any way, as far as I know, to ask for images taken at different times for the same point. I don't know whether this limitation will be lifted in the future, but this will be the key step for recognizing tree species, in my opinion.
Many thanks.
Thank you, Giorgio. There is some other question? Oh, non vedo mani alzate. Okay, no, I'm just a curiosity. According to your opinion and to the review that you performed, how far are we from a fully automated method or a fully automated algorithm that may completely exclude the human activity and the human intervention. So it's something that is just a matter of working on algorithms. It's just a matter of finding the right way or the right mix of sources that is needed, or is needed something more deep, like a complete change of view about this field. So it's an algorithmic point, or is it something that under the research objectives is missing?
I would say for most variable of interest is mostly an algorithmic point. So I can envision more accurate algorithms and more accurate sensors being able to deliver automatically 3 location points, 3 heights, and possibly delineate, well, not 3 crowns maybe, but canopy cover areas with a high spatial resolution in urban settlements. For species identification, I think human intervention is still required in order to train the computer to associate a certain spectral response to a given species. So there's no way that I know of to completely automate 3 species identification. Of course, the more detailed ground inventories of trees, for example, those provided by city administrations, can already be, I mean, they are a human intervention, but if they are there already, they can be used once, and the first time, for species identification and tree location. And then these should not change very much through time, unless, you know, trees die or are replaced. So, I mean, if by human intervention you also include inventories that are already existing, then yes, human intervention is needed. But in cities with very good data, I think fully automated measurements is possible.
Thank you very much for this answer. So there are other questions? So no other questions, no raised hands, nothing. Okay, so we can...
Well, sorry, this is Mark. I have one question. Is there much historical data available as to say what the situation was in a given city 20 years ago? Is it complete enough, or, and if there is such data?
Hardly. The only source, well, unless a given city has a very old urban green inventory, which I doubt, the only data source available would be Landsat or MODIS. So coarse resolution satellites. Landsat is 30 meters and MODIS is 250 meters on the ground. MODIS is active since year 2000, and Landsat, as I said, since the mid-70s or beginning of the 80s. So with these, you can have a very nice time series of land use and land cover, but you wouldn't be able to do anything about individual trees because the resolution would be just too coarse. So unless some archival data are maintained by a city, but 20 years is a long time. I really doubt that you can find it.
Thanks.
Thank you.
If you do, tell me.
Okay, other questions? Okay, so let's thank you very much, Giorgio, for this nice and very interesting presentation.
Thank you.